Alright, we'll continue with problem 4.17. I'll skip problem 4.17. You can do that as homework. I'll start from problem 4.18. We are asked to find the nines complement of a BCD digit and a gray code digit. Let us write down the truth table to find the nines complement of the BCD number. Let the input BCD number be ABCD and the output BCD nines complement be WXYZ. BCD numbers go from 0 to 9, and the 9's complement you subtract the number from 9. So 9 minus 0 is 9. 9 minus 1 is 8. 9 minus 2 is 7. 6. 5. And then using the truth table you can write it. You can write WXYZ as functions of ABCD and when you're writing the K map, we assume that 1010 to 1111 these input combinations are don't care. From that we'll get W is A prime, B prime, C prime, X is B XOR C, Y is C, Z is D prime. We have W, X, Y, and Z. Part B, we have to do the same thing, except that now we have a gray code. So decimal 0 in gray is, well, let me take some other number. We had seen gray codes in a previous lecture. So 2 is ninth complement of 2 is 7. 2 in gray code is 0011. 7 in gray code is 0100. So that's how you will have to find the ninth complement in gray code. And you do that for every single possible gray code combination. 4-bit gray code number. And you'll get, here's gray code and its ninth complement. Gray code bits are represented by ABCD. Ninth complement is WXYZ. And the corresponding ninth complement will be next we simplify using K-map. And we are finding nines complement. You can't find nines complement of the number 10, 11, 12, 13, etc. I mean, you can do it, but uh, you'll have to take, well, we are trying to find the nines complement of decimal digits. So only one decimal digit. So we'll only consider from 0 to 9. Similar to 2's complement, 9's complement also exists for multiple digit numbers, but we are only concerned with single digit decimal number. So again, you can take don't care 8, 9, 10, 11, 14, and 15. These combinations don't appear in this table on the gray code side. So those are all don't cares. We don't care about the number, about those numbers. And if you simplify using K-maps, you will end up with the following. For which again you can write down the logic diagram on your own. Problem 4.19. Sorry, give me a minute. Let me try to fix my mic. Problem 4.19 is the following. Construct BCD adder subtractor circuit. Use the BCD adder of figure 4.14 and the nines complementer of the previous problem 4.18. Use block diagrams for the components. Let me get figure 4.14. Give me a minute. Ah, how do I share this image? Okay, this is the. Let me crop this. This is the BCD adder circuit that we have. We have a 4-bit binary adder with carry in and some combinational circuit from the output of the 4-bit binary adder and the carry out, and that is fed as. So the logic here is that if the sum of two numbers exceeds 9, then you can get the first digit of the BCD number by adding 6. So that is a BCD number is only from 0 to 9. So let's say you add 9 with 9. The result is 18. But in BCD representation, you can't represent 18 with one group of 4 bits. So for 8, you need a group of 4 bits. That's 8. And the 1, you need another group of 4 bits. That's 1. So 9 plus 9 is 18. Is represented in BCD in that way. Now, if you simply add 1001 with 10101 using a binary adder, you will get 1 plus 1 0, 1 carry, 1 0, 1 plus 1 0 with 1 carried over. So you get 1 carry with 0010, which is not the same as this 8 that you needed. It's actually 2. But if you see that if you add 6 to this, you will get 6 plus 2 is 8, so you'll get 1000. So if there is an overflow, then you need to add 6 so that you get the right digit. And why do you need to add 6? That is because if you want to carry over, if the suppose you add 9 with 9, you get 18. How do I say this? So any number I'm not sure how to tell you this. Okay, let's say the sum of your digits is within 9. Then you can represent it by 4-bit binary number from 0000 to 1001. Suppose it was one more and the sum of your digits was actually 10. When you get 10 in BCD, that means you have a 0 in the units place and 1 is carried over. And carrying over a 1 in the BCD number can be done by adding 6 to the binary number, because if you add 6 to 9 you will get 15. If you add 6 to 10 you will get 16, which will be which will have zeros in the first four positions, and the 1 will be carried over to the fifth bit. Maybe I should write that down with an example. So let's say you add 1, this is 9 plus 1, the sum exceeds 10, you start counting again from 0, and there's a carry of 1. We ignore this carry if it's only one digit addition. Anyway, after 10 you start counting again from 0. So similarly, in binary, after 15, say if you add 1, this will be 10, 1010. Next will be 1011. Next will be 1100. Then 1101, 1110, 1111. And then once it exceeds 15, there will be a carry and it will start counting from 0 again. So in decimal, when it goes to 10, you have to restart from 0. In binary, you will restart from 0 when you go to 16. So you add a 6, right? The difference is 6. So whenever something exceeds 10 in decimal, you want to reset and start again from 0. That can be done by making the binary number exceed 16 by adding 6. So it will reset to 0 and start again. I hope you understood the point here. I don't have a better way of explaining it. Anyway, so that's the 4-bit BCD adder. Now using this, they want us to construct a BCD adder subtractor circuit. Similar to binary numbers where subtraction is done by 2's complement, where to subtract a number from another number, you add the 2's complement of the number which you want to subtract. So that can be done in any base system, even in decimal system. So again, similar to the binary case, you take the 9's complement and add 1 and add that number to. So what you can do now is have a quad 2:1 multiplexer. That is, it multiplexes two groups of 4 bits at a time. And if you want to do addition, then you pass on the values B0, B1, B2, and B3. If you want to do addition, you select m is equal to 0. It will select the first 4 inputs, which are B1, B0, B1, B2, B3 directly. If you want to do subtraction, you select m is equal to 1, which will select the next 4 inputs. The mux will select the next 4 inputs, which are 9's complement of B0, B1, B2, B3. And this output, you add it to your BCD adder, you give it to your BCD adder, and the carry in is, again, if it's addition there should be no carry in, if it's subtraction there should be a carry in, and you add that to A0, A1, A2, A3, and that will give you the sum S0, S1, S2, S3, and your carry C out. So that is how, similar to binary addition, you can get a full adder BCD also using the same logic. Problem 4.20. For a binary multiplier that multiplies two unsigned 4-bit numbers using AND gates and binary adders. So design a circuit using AND gates and binary adders. So the 4-bit, sorry, the binary adder that they're referring to is from figure 4.16, and this is figure 4.16. It's a 4-bit by 3-bit binary multiplier. So you have a 3-bit number A0, A1, A2 and a 4-bit number B0, B1, B2, B3. So the logic again here, when you are multiplying a number B0, sorry, B3, B2, B1, B0, let's say, let me write it down here. You have B3, B2, B1, B0 and you multiply that with A3, A2, A1, A0. How do I do that? What you do is you multiply B3 B2 B1 B0 by A0. So you get B3 A0 B2 A0 B1 A0 B0 A0. In binary number, what does it mean to multiply by A0? If it is 0, its number turns out to be 0 0 0 0. If it's 1, the product of 1 with B3 B2 B1 B0 is simply B3 B2 B1 B0 itself. So it's an AND operation with A0. Then you shift by one place. A1 is in the 2's place. So you shift to one place, one place and multiply again. You get B0 A1, B1 A1, B2 A1, B3 A1. Then you shift by two places and do the same. B0 A2, B1 A2, B2 A2, B3 A2. Finally you shift by three places. B0 A3, B1 A3, B2 A3, B3 A3, and you sum all these things up. So B0 A0, B1 A0 plus anyway you sum this up. The way they do it is the first digit is simply B0 A0. You have B0 A0 B0 here. That's the first digit. Second digit is B1 A0 plus B0 A1. Yeah, you have B0 A0 B1. You have B1 A0. Second set will give you B1 A1. So what they're doing here is they're adding this number with a 0 here. 0 0 0. So this number and this number they will add using the first adder. Alright. And the second digit is nothing but the LSB of that sum. Okay. So from the first adder you have, you will get the second digit. Then they'll take whatever sum you get there, they will so you'll get the sum, they will ignore the LSB, the sum of this, sum of this part with a 0 or with the carryover they will add to this part. That sum will leave you this bit. Then they'll take sum of all these, they will add it to this part. So that sum will give you the last four digits with carry. So here it's only three stages. You just need to append one more stage, that's all. This C0 you keep it as it is. C1 you keep it as it is. C2 also you keep it the same. Then C6, C5, C4, C3, you give these four as the first input of a 4-bit binary adder, along with the product of A3 with B0, B1, B2, B3, and the sum of that will give you C0 dash, C1 dash, C2 dash, C3 dash, C4 dash, C5 dash, C6 dash, and the carry out C7 dash. So that's how you extend it. Now using this you can extend it to 5-bit by 4-bit multiplier, and then using that you can extend that to 5-bit by 5-bit multiplier, and you can keep on doing this until you're satisfied. The only problem with this type of circuit is that there are a large number of stages, and you need a lot of adders. Problem 4.21. Design a combinational circuit that compares two 4-bit numbers to check if they are equal. The circuit So the naive way to do this is write the truth table and get the expression that you want. Only problem with that is there are two 4-bit numbers. So 16 possibilities for the first number and 16 possibilities for the second number, and in total 16 into 16, 256 entries in the input side. If you write the truth table directly, Or what you can do is the following. Let the two numbers be A3, A2, A1, A0 and B3, B2, B1, B0. The numbers are equal only if A3 equals B3, A2 equals B2, A1 equals B1, A0 equals B0. So if A3 equals if AI equals BI for I in the set 0, 1, 2, 3, then AI XOR BI whole complement is 1. So the function to check if the numbers are equal is simply equal if A0 XOR B0 complement, that is this AI XOR BI complement is 1 for all I. So the function is simply the following. And the circuit is just XNOR operation. We'll go to problem 4.22. Hello. Alright. Final one or two problems in this session. Design an XS3 to binary decoder using the unused combinations of the code as don't care conditions. And we write down the truth table. Can write this as XS3 for short. BCD, not BCD, it's binary. So 0, 1 and 2 are invalid combinations, so we can take them as don't cares. 3 is 0, 4 is 1, 5 is 2, 6 is 3, 7 is 4, 8 is 5, 9, 10, 11, 12 are 6, 7, 8, 9 respectively. And then the remaining numbers 13, 14 and 15 are all don't cares. So using the about truth table we can simplify using K maps. A is summation of 11, 12. B is summation of 7, 8, 9, 10. C is the summation of 5, 6, 9, 10. D is the summation of 4, 6, 8, 10, 12. D don't care is 0, 1, 2, 13, 14, 15. And you will get A is Wx plus Wyz. B is x prime y prime plus x prime z prime plus xyz. C is yz prime plus y prime z, which is y XOR z, and D is z prime. You can write the logic diagram yourself. That's it for session 7. I'll see you in session 8 and we'll pick up where you left off.